Look at the tangible, everyday objects around you right now. The chair you're sitting on, the screen you're watching, the coffee mug resting on your desk. At their most basic level, these objects represent matter, anything that occupies physical space and possesses mass. That mass is a precise, constant metric of exactly how much matter a specific physical body contains. Whether that coffee mug is sitting in your room, deep underwater, or floating out in deep space, its mass remains exactly the same. We routinely confuse mass with weight, but in physics, they represent entirely different concepts. Weight measures how much gravity pulls on an object's mass. Look at this astronaut carrying heavy equipment boxes across the lunar surface. Because the moon's gravity is a fraction of Earth's, those boxes weigh far less there, even though the amount of matter inside hasn't changed. Relying on weight alone gives an incomplete picture of an object's nature because it changes based on the environment. Understanding the physical reality of matter requires observing it at a scale where these external variables don't dictate the rules. This outlines the rules governing the three states of matter. A solid maintains a definite shape and volume. A liquid keeps a definite volume but flows to fill its container. And a gas has neither, expanding freely to fill any available space. These rules change under extreme conditions. Expose a gas to high temperatures and you create plasma, an energetic state of matter found in stars and these violent solar flares. On the opposite end of the spectrum, matter frozen in a laboratory to near absolute zero can form a Bose-Einstein condensate. At these temperatures, individual atoms lose their separate identities and behave as a single quantum entity. Our daily experience only reveals a narrow window of these five states. The physical reality we interact with is governed by mechanical rules that operate far below the surface of what we can see. If you push the camera close enough, past the physical boundary of a tangible object, you enter a hyperactive microscopic universe. It is a void filled with entirely separate, deeply restless particles. The existence of this hidden layer was conceptualized centuries before modern science could prove it. Around 600 BCE, Indian sage Kashyapa proposed matter was built from tiny, indivisible particles called anu, a concept echoed later by the Greek philosopher Democritus. While these ancient thinkers identified the building blocks, modern physics reveals their behavior. They are never still. Through a process called Brownian motion, these microscopic particles are locked in a state of constant, random frenzy, endlessly smashing into one another. This relentless kinetic energy drives diffusion. And when you watch food coloring spread through a glass of water, you are seeing billions of invisible particles bombarding each other until they are evenly distributed. This microscopic movement dictates the macroscopic form. Massive interparticle forces pull particles into the tight, vibrating clusters seen here on the left to form a solid. On the right, the attraction is incredibly weak, leaving the particles widely scattered and freely moving as a gas. Even a seemingly motionless object, like a heavy glass pitcher, functions as a vibrating cage. Its particles are trapped in place by these forces, humming with kinetic energy that never stops. Every piece of matter in this invisible world is composed of elements. An element is the simplest building block. It cannot be broken down any further. We currently know of 118 distinct types, from hydrogen to carbon to oxygen. Physical mixtures like dirt stirred into water allow each component to keep its own properties. Chemical compounds involve a different process, a formal combination that yields something entirely new. These compounds do not merge randomly. They lock together under strict rules, forming exact mathematical atomic ratios. This 2-to-1 ratio is what defines water. Every single molecule in a glass of water consists of exactly 2 hydrogen atoms chemically locked to 1 oxygen atom. Oxygen actively supports burning, and hydrogen is wildly combustible. Yet forcing these two explosive gases to combine in that specific ratio produces a liquid that extinguishes flames. Chemical rules do more than just mash properties together. They act as a system that completely rewrites the physical nature of the substance. Adding heat triggers a predictable sequence. Melting ice becomes liquid. Continued heating causes evaporation into gas. Removing heat reverses this. Cooling vapor condenses back to liquid, then freezes solid. Under specific conditions, matter completely bypasses the liquid phase, turning from solid straight to gas through sublimation, or gas to solid through deposition. This entire macroscopic cycle is dictated entirely by how much energy is applied to those restless, microscopic particles. Every physical thing in our universe is a temporary arrangement of atoms. They are held together by invisible forces, simply waiting for a shift in energy to transform into something entirely new.